Okay, hello, Marissa, and anybody else who is interested in lesson 25. Probably one of the most misunderstood concepts in physics 20 and one of the most difficult to understand. So we'll go through it and see if we can clear things up. It's Newton's third law. For every action force, there is an equal and opposite reaction. And the example they have in your notes is a pretty good one. It says you push on the handle of a lawnmower to make you go forward. It will push back against you in the opposite direction with as much force. So you have to think about, in that example, you have to think what's making the lawnmower move. It's not your hands pushing on the handle. It's your feet on the ground that are making the lawnmower move. It's the friction on your feet. And since you push back on the ground, it pushes you forward. That's what's making the lawnmower move, not your hands. Your hands and your arms essentially become an extension of the lawnmower. So this is where Newton's third law gets a little confusing. And then in the notes, it talks about action and reaction pairs. So what's causing the action and what's the reaction? And here's some great examples here for you. Number one, the tires. The tires on a car push on the road. The reaction is the road pushes on the tires. I think an even better one, number two here, is it's a great example. While swimming, you push the water backwards, and therefore the water pushes you forwards. So you have to consider what two things are acting. Another good one right here, action, a rocket pushes out the exhaust, and the exhaust pushes the rocket forward. So the exhaust is always going in the opposite direction as the rocket. And then the last one, an apple pulls down on the earth, the apple pulls up on the earth. How can this be true? And in fact, it is very true. It's hard to comprehend that as an apple falls towards the earth is accelerating up towards the apple. But in fact, theoretically, that's what happens. So let's do this example here. It says if an apple has a mass of 2 kilograms, determine the acceleration of the earth. Okay, so first we're going to calculate the force of the earth on the apple. And for that, we can simply use F equals ma. The mass of the apple is 2 kilograms, and it's accelerating towards the earth at 9.81 meters per second. And therefore, the force of the earth on the apple is negative 19.26 newtons. So Newton's third law says for every action, there's an equal and opposite reaction. So the force of the earth on the apple must be equal and opposite to the force of the apple on the earth. So we can say, therefore, the force of the apple on earth is equal and opposite. So it's positive. In other words, the apple is pulling up the earth with a force of 19.62 newtons, which is completely true. Now the question is to determine the acceleration of the earth. So that's the force of the apple on the earth. Then the acceleration is going to be the net force divided by the mass. Net force we just calculated. Of course, the mass of the earth is unbelievably big compared to an apple. And so you can see what's going to happen here. We're dividing a relatively small number by a huge number, and therefore we are going to get a very, 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 very small acceleration. It turns out to be 3.28 times 10 to the negative 24 meters per second squared. So the Earth is accelerating towards the apple with that acceleration. Of course, it's so unbelievably small. There's no way you could feel it, and for all intents and purposes, it doesn't happen. But that's the theory behind it. Okay, that's why we can say that there's an equal and opposite force. Let's move on to example 2. Example 2 says a rifle fires a bullet. The force of the rifle exerts on the bullet is exactly the same, but in the opposite direction. So if you've ever fired a gun, I've never fired a gun. I wouldn't touch a gun if my life depended on it, or maybe in that case I would. But if you've ever fired a gun, you know that when you pull the trigger, what happens to the gun? It goes backwards, right? It's the kickback or the recoil, and that's why if you're firing firing a rifle, you have to have it right against your shoulder, because if you don't, you could come back if you hit your shoulder and could dislocate or injure you quite seriously. So if you're going to fire you've got the bullets coming out of the rifle. It's going to exert an equal and opposite force. What do we have here in this problem? We have the mass of the bullets, 15 grams. We have the mass of the rifle, 6 kilograms. So right there, you can tell what's going to happen. It's the rifle that's kicking back that has a mass of 6 kilograms. The bullet is going forward, has a mass of 15 grams. Obviously, one of them is going to have a huge acceleration, and the one's going to have a much smaller acceleration. The bullet is going to have a very big acceleration because it has a very small mass. The rifle is going to have a smaller acceleration because it has a big mass. The bullet leaves the 75 centimeter long rifle, moving at 70 meters per second. So first of all, we have to determine the acceleration of the bullets, and we're back to kinematics for that. We have the initial velocity. We have the final velocity. We have the displacement, 0.75 meters, and we want to find the acceleration. So our old favorite, acceleration therefore equals vf squared minus vi squared divided by 2d, and you stick those numbers in and you get the acceleration, which turns out to be 3.3 times 10 to the 3 meters per second squared, which is the acceleration of the bullet, which you would know a bullet accelerates at an extremely high rate. So next we're going to determine the force of the rifle on the bullet. So that's just going to be F equals ma. Right, on the bullet, and so we need the mass of the bullet. The mass of the bullet is 0.015, and the acceleration of the bullet is 3.3 times 10 to the 3. And if we multiply those together, we get this, 49 newtons. So that's the force of the rifle on the bullet. Therefore, I'm just going to put here, therefore, the force of the bullet on the rifle equals negative 49. Newton's third law. Every reaction is an equal and opposite reaction. So if there's 49 newtons of force by the rifle on the bullet, then there's negative 49 newtons of force the bullet on the rifle. And determine the acceleration of the rifle, same as our previous problem. Acceleration equals the net force divided by the mass. Here it's negative 49 or just 49. It's irrelevant as long as you say it's going in the opposite direction. Divided by the mass, and now of course we're talking about the acceleration of the rifle, so we want the mass of the rifle. You divide those and you get negative 8.2 meters per second squared, which is obviously considerably less acceleration than the bullet, but still it's going to hurt you if it hits you in the shoulder. And then D, is there a D here? D. Oh, D, I have D in the notes, but not there. So the D says, explain why the bullet accelerates more than the rifle and the force are the same. I think we kind of explained that the bullet has very little mass, so it has a huge acceleration. You could sum it up like this. Oh, there. Oh, no, there. You could say this. The forces are equal. If this is the force of the rifle on the bullet, and this is the force of the bullet on the rifle, they are equal. So these F's are the same size. For the rifle on the bullet is very small, has a very small mass, therefore it has to have a huge acceleration. The rifle has a much bigger mass, therefore it must have a much smaller acceleration. So for these two forces, this one here to be the same size, to be equal and opposite in magnitude, then you have to have this relationship. If one has a low mass, has to have a high acceleration. Has a high mass, has to have a low acceleration. Okay, moving on To example number 3, you just got a couple of identical 20-kilogram shopping carts to do some shopping. The reason you have two is they're unfortunately stuck together. You push them into the store to get help pulling them apart. You're running towards the store, accelerating the shopping carts at 1.2 meters per second squared. Determine the force the second cart exerts on the first. This is more of a theoretical question than anything. It's actually very simple. The force equals the mass times the acceleration. The acceleration is given to you. It's 1.2. All you need to do is decide, what do I use for the mass? I have two 20-kilogram shopping carts, but the question says, determine the force the second car exerts on the first. Well, the second car can only exert a force with its own mass, so you simply use 20 here. That will give you your answer, which is 24 newtons. And there's 24 newtons. The force the first car exerts on the second is 24 newtons, and the force the second car exerts on the first is negative 24 newtons. So that's one way you can look at it. Then it says, once you get in the store, you see an example pushing two boxes out of the store, stockroom. The employee is pushing with a force that causes the two boxes to accelerate at 1.12. You know that the friction acting on the box of dog whistles is 14.8. Determine the force the dog whistle box is applying against the Rice Krispie box. Okay, so if I do a free body diagram for the dog whistle box, I have an applied force pushing it this way, and I have the force of friction pushing it that way. And so for this one's a little more intricate than the other one. For this one, I have to find out what this is first, what the applied force is, because it's not given to me in the question. So I'm going to use a net force, and here I have two forces acting on it. I have the applied force and the force of friction. So my net force acting on the dog whistles is going to be my applied force plus my force of friction. And the one that I'm solving for here is my applied force. So I could rearrange this if I wanted. The applied force equals the net force minus the force of friction. Now take into account when you're doing this, the net force is in which direction? The net force is obviously going to be in that direction. The applied force is also in this direction, but the force of friction is opposite. It's in that direction. So you have to make sure you're careful with the signs on this one. All right, so my net force, I can expand on that. My net force is going to be the mass times the acceleration. Fa equals ma minus ff. And again, you got to be careful on this one. What am I going to use for the mass? Well, I have to use the mass of the dog whistles box because it can only apply a force with its own mass. 2.36 times the acceleration, 1.12, minus, and take into account here, remember that this is negative, so it's going to be minus negative 14.8. Minus negative 14.8, and if you do all that, you get an applied force of 17.4 newtons. So that's your answer. You could say that's the answer that the dog whistle box is applying to the Rice Krispie, and the Rice Krispie box is applying to the dog whistle in an equal and opposite direction. Okay, that one's a little tricky. And then the last question, if I push on the lawnmower, it pushes back on me with an equal and opposite force. Explain why we don't just stay still. I think I explained that at the beginning of the lesson. It's because you are pushing on the handle, it's pushing back with you with an equal and opposite force, but you essentially become part of the lawnmower. What's making the lawnmower move forward is your feet the ground is providing friction for your feet, and you push back on the ground. And what does the ground do? It pushes you forward. And since the lawnmower is attached to you with your arms and your hands, then everything goes forward. Okay, so I hope that gives you an explanation of lesson 25. As I said, it is one of the trickier lessons probably in the whole year. There's nothing on your assignment, or there's very little on your assignment related to Newton's third law, just theoretical questions. And that's really what you need to know, is you really need to know just the theory of what it is and how to explain it. So there's not a lot of mathematical applications of it that you will be tested on in this year or next year. So that's Newton's third law, and stay tuned for more lessons coming up.